Hello, I'm Joseph Schulte, and this is a short presentation on a project I'm part of in the LTU Actor Vehicle team. The purpose of this project is to give our vehicles the ability to predictably and reliably follow people and vehicles autonomously with the available sensor equipment. Ultimately, our motivation is to allow for more natural and flexible interactions between humans and machines. After all, the future of technology isn't humans and machines existing in separate worlds, it's intelligent tools deeply integrated into our everyday life. The immediate resources available to us on the vehicle are a camera and a computer. From there, we can use a neural network named YOLO, for You Only Look Once, to interpret what the vehicle sees and identify objects of interest in line of sight. Using only the visual data, we can estimate the location and distance of the target and control the car to follow. While our primary interest is humans and vehicles, neural networks are extremely flexible. The pre-trained YOLO network we're using can also detect stop signs, animals, cell phones, so on, and it's easy to fine-tune or train our own network if we need something special. In order to control exactly who or what the vehicle follows, we need to give it some identifying signal or mark. For that purpose, we use Aruco markers, which are similar to QR codes but optimized for spatial vision processing. The target simply holds up the marker and the vehicle knows to follow them. Once the target is marked, the vehicle can keep track of it specifically with a simple movement-based algorithm. In the lower right, you can see a diagram of the different nodes in the program and how they communicate. So each bubble is a node and each arrow is a line of communication. Here is a video demonstrating our vehicle following someone. So the first conclusion that we drew was computer performance is critical. Neural networks can be very efficient for what they do, but they're still a demanding computational task, so we need to equip the vehicle with a more powerful computer, or needed. Most critical part of the computer was the GPU. Next, we found that the bulk of the work went into tuning tracking consistency. A large part of this was keeping track of a single target so it didn't get confused by crowds. Next, as digital cameras are much less adaptable than human eyes, we found that setting up the camera for the ambient lighting conditions was also key. Going forward, it'll be important to implement automatic exposure and focus adjustment suited to this application. In terms of the vehicle's behavior, we found that the most significant factor was the ability to maintain a single target. Once we got that figured out, its behavior became extremely predictable. For the next stage, we will need more accurate distance information than the 2D camera can provide. Vehicle's 3D LiDAR is perfect for this purpose, as once we integrate it into the program, we will be able to resolve distances to within 3 centimeters of accuracy. Thank you for listening.